Today we're doing a radioactive physics lab, and with radioactive materials, the danger is much greater if you have the radioactive material in things that you're going to ingest. So before I bring in the samples, I'm going to ask everyone to take everything they ever intend to put in their mouth, whether it be chewing gum, water, food, and put it outside the costume before I bring the radioactive samples in. Now, the samples themselves are of fairly low activity. You might disagree when you see the counters go crazy, but compared to what we consider radioactive samples, they're very low activity. So they're a very minor health concern, so you shouldn't be worried about health at all. But we're still treating them like you always do with radioactive materials. You always make sure there's no anything ingestible in the presence of the radioactive samples. Now, before we get started, today's lab requires 15 minutes of background count and then 91 minutes of lab time. And you should be ready to walk out the door when you get done with that 91st minute of lab time. We'll do the background count while I'm doing the introduction. So let's just get you set up with that. We're going to have only 6 groups. So that will be 2 groups of 4 and all the rest, and 4 groups of 3, right? 3. So choose up your groups now, and let's get started with the background counts. So the top 3 on either side are the groups. So if you 4 are together, you should all come together. I mean, after we get the background started, you can separate for all I care and then come back together. But we want to. Yeah. Okay, so we have one group of 4 here, a group of 3 there. Are you guys a group of 3 there? And then we have all the rest of the groups still need to form up. So one more group of 4 and then the other 3. Okay. I want them out of the room when we get to that point.
Yeah.
Okay. Do that right now?
You don't have to do it right now. I want to make sure everyone's aware, and not have like, oh no.
Nobody takes my trail spots out there.
Okay, so now that we broke up into groups, one more thing that I kind of need to make sure I remind you. I heard somebody say, good, then we can work on a project. We have to have the posters done by Friday, no later than 3 p.m. 3 p.m. is when Dr. McNeil is going to be physically driving over to UNL to deliver them. So we have to have them to her before 3 p.m. on Friday. So I want to make sure people are aware of this and not like, Thursday night. Wait, what? Everybody got the message, right? Okay. Now, to start the background count, you already have them set up, they're powered on, and the voltages, Yafet set them all, and I went around and made sure that they were all counting. I didn't look where he said it. If they're counting, we'll consider it good, right, Yafet? Right. We have in here Geiger-Muller counters. I think they're Geiger-Muller. I don't think they're scintillation detectors. And they are basically, they make an electrical pulse anytime a radioactive particle, like in this case, beta particles, hit it, and then it's counting the pulses. And we have radioactive materials around us all the time. Like if you look at the machine in front of you, what number does it say for the counter? Okay, so that's how many counts it is counted in about 20 minutes. So that's radioactivity that's around us that's picking up. Not very much, right? You can sit there and say, 5 seconds and it ticks 1. Well, we need to do a background count so we can take this out of our data, what's occurring naturally, and so we're only looking at the sample. Now, of course, the background data is not very fast, and the uncertainty is proportional to the square root of the number of counts, what's equal to. And so if you have 100 counts, then your uncertainty is 10, which means that you have 10 out of 100, a 10% uncertainty. Where if you had 1,000 counts, then you would have, square root of 1,000 is what, 30? And so it'd be about a 3% uncertainty. And so the more counts, the lower your uncertainty. Well, we're going to only do for 15 minutes and assume that's going to be enough counts. It should be somewhere in the ballpark of a couple hundred. So what I want you to do now is you have a button on the right-hand side that has 3 settings: 1 minute, count, and off. So turn it to off or stop. Yeah, stop. And then right beside that, there's a button that says clear. Just press that button. It won't stay. It'll just clear the number. Reset, really? I totally have these words down. If you go ahead and correct me on the last word as well. Okay, no, we actually have them. So now what you're going to do is you're going to do a 15-minute background timer. So you need a timer. You can use the timer on the computers. You can use a timer on your phone. I would use the timer on your phone, set it to give you an alarm at 15 minutes so you don't let it run by and forget to turn it off. And then you just want to start the timer at the same time you take the right hand button and move it from, let's go stop to run. Does it say run?
No. Continuous.
Continuous, okay. So at the same time you start your counter, go to continuous, and then just let it run, and I will lecture. So I'm going to stop until everybody says, yeah, we got that. So just going to do a poll. Do you have yours going, Jonathan? Not yet. Okay. Okay, got it going? Do you have yours going, Aaron? Do you have yours going, Paris? Yeah. You have yours, Caitlin? Okay, so everybody has the background count going. This time here is otherwise lost time anyhow. Now I get to talk about how the theory works and what we're going to do to analyze the data. So in theory, if you have a radioactive nucleus, you have a nucleus that's unstable. That nucleus is kind of like I have this pin, and I'm kind of iffy on balancing. Okay, I have it balanced on the end. It's in a stable equilibrium, right? But not very stable. If I hit this thing harder, well, you get the picture. If Jerry teases me about my soccer team being horrible, and I slam the desk hard enough, okay, forget it. It'll fall over, right? Okay, yes, that's just a more stable nucleus. If it's more stable, it's going to be a longer time before it's likely to decay due to some random activity. So some are very unstable. That's like balancing on the point here. Some of them are more stable, but still ultimately not stable like that. So basically, you could say every second there is this percent chance that it will decay, fall to a more stable arrangement, and release energy in the process. Because if you go from higher energy to low energy, you can't create or destroy energy. The energy's got to go somewhere. And so that's what we're measuring, is the energy coming out in the case of today's experiment with an electron. So we can make an equation that says the rate at which I'm going to have my decays occur is equal to a probability number that we call the decay constant multiplied by the number of actual radioactive nuclei present. Does that make sense? So if I have like 100 nuclei, I would expect to have more decays per second than if I only had 10 nuclei, because I have more that could be decaying. Taking that, using a little calculus, and I don't know any other way to do it than calculus. I think that's because there really is no legitimate way. The rate is minus the change in radioactive nuclei per time. That D, remember D just means change in. It's delta, but it's for very small deltas is when we use D. So the rate is minus dN dt. If I put this substitution in there, I have an equation that says lambda n is equal to minus dN dt. The people in my Physics 252 class have done this many times now. You separate variables and integrate, and you end up with an equation that says the number of radioactive nuclei at any moment, n, is equal to the number you started with multiplied by E, that's 2.7 whatever, so just a constant, time raised to the minus lambda t, where lambda is that decay constant. And going back up to our first equation, since the rate of decay is just the decay constant times the number of nuclei, that equation is exactly equivalent to saying the rate is equal to the rate you started with, e to the minus lambda t. So for our experiment, you're going to be measuring the count rate. You're going to be measuring how many counts per minute you receive. So your timers, you're going to make timings for 1 minute. Now you'll notice the timing have a setting for 1 minute. And normally I would say, hooray! Except for my first year here, I had students use that setting. And what I found was 1 minute could be 54 seconds and then 102 seconds, well, not 102, and then 67 seconds. That it wasn't the same amount of time each time period. And that screws everything up. So because of the inconsistency in the timing of these things, I'm going to have you measure the time manually. So what you're going to do after the background's all done, then I'm going to bring in radioactive samples. At that time, we need to make sure all the food, anything, gum that you're going to stick in your body is not in the classroom. And then you're going to put the sample in there. You're going to start a stopwatch and simultaneously start your first count. You will not mess with the stopwatch again. You let it run continuously throughout the experiment. If you ever stop the stopwatch, you've also stopped your experiment and have to start over at the beginning. Right? So don't stop it. Yes, I want everyone to understand this. Also, make sure you write down your data as you get it. I had one group that was more than an hour into this experiment. They were using plug-in computers, and somebody walked by and accidentally pulled the plug out of the wall, and they hadn't written down their data. And you can't tell them, oh, that's okay, because they weren't following the procedure. A scientist writes down their numbers when they get them. And so they had to do the whole stinking experiment over because they'd done it wrong and lost their data. Right? It's a horrible lesson to learn. Okay, so you started counting at the same time you started the stopwatch. You're going to count for 1 minute, leave the stopwatch running, but stop the counting at 1 minute. Then you'll write down the number of counts that you got from time 0 to 1 minute. You're going to record that in your data as starting at time 0. So at time 0, I had this many counts. Then you're going to take, well, how many counts do we have background? You're not done yet, but you'll have some number. How many counts per minute is that? If you count for 15 minutes and you want to know how many counts per minute, how do you convert? It's really tricky. Yeah, divide by 15. Did you say divide by 5? Divide by 15. So you're going to take that background number, divide by 15, and then for each measured activity, you're going to subtract that count rate. So if you had for the first one 3,765 and your background was 15 counts per minute, you would take that 3,765 and subtract 15 to get the background corrected rate. And then you're going to make a graph, 2 graphs by hand. One graph just using this regular old paper, and one graph using semi-log paper. I have 2 versions of the semi-log paper, some that are 2 decade and some that are 3 decade. If your first measurement is over 10,000, then you'll need to use the 3 decade one. If it's under 10,000, then use the 2 decade one. And so now I'm going to spend the rest of my time here talking about how to make a graph and how to find the slope. So, actually I'll come back to this. There's one more thing here. So here is an example of the 2 decade. It says here 2 cycle. You see up here. It's truncated. The top part's missing. It's on the paper missing as well. It's 2 cycles. That's 2 decades going from 1 to 10 twice. Over here on this side, you can see the vertical axis is going 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it starts over. You're going to take these, and each one, you're going to multiply by a multiplier. So take your highest number. If your highest number is, let's say, 3,765, I think that's what I used before, then I'm going to want my upper 3 to correspond to that. So I'm going to take this upper decade, oh goodness, and multiply this times 10 to the third. So this is going to be 1,000, 2,000. Okay, I missed a 0. 3,000. Or I guess the way that they're labeled for like 1 through 4, I could put them in line. So notice that it's not going by the same spacings. The distance between 1,000 and 2,000 is bigger than between 2,000 and 3,000. This paper has an uneven scaling because it's spaced logarithmically. So we call it log paper because it has logarithmic spacing rather than a linear spacing. So if this number is 1,000, what's this number going to be? 900. So these are times 10 to 1 less than the one above. So this is 900, 800, 700, and so on. So the bottom one down here would be 100 then. So that's how you're scaling the vertical axis. The horizontal axis for everybody is going to go 0, 10, 20, blah, 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 90 with time in units of minutes. The vertical axis will be background corrected activity. Activity is radioactivity, number counts. And so the units are counts per minute. And then, of course, you'll want to have a title at the top. So you can scale your paper as soon as you have your first data point. Then you put the data points, you don't whip out the calculator here. The only calculation up to this point is subtracting your background count from the measured number. And so using my example, once again, I said 3,760 for the background corrected. So 3,000, each one of these lines is going to be 100s if it's 3,000. So 2 is there, 4. So that's 3,600. I think it's 3,760, right? 760 is right about there. So the first one is going to be there for my data. So I make the dot, put a circle around it. I'm pretty sure you can do all of this in less than 4 minutes, right? So do the same thing on your linear paper. Once again, no calculator involved. You just put something just above your first measurement up here going down to 0 at the bottom. So choose your vertical scale. Your horizontal scale, once again, should go out to 90, 0 to 90, and plot your data on there. Then you wait, hit the, don't do this now, but you'll hit the button to reset the counter. And when your timer gets to 5 minutes, you'll hit the start button, well, continuous, on this at the moment that your timer gets to 5. And then when it gets to 6, you'll go to stop, write down the number, repeat to add the point to the graph. There's a lot of downtime here, right? And you've got, for 2 groups, 4 people in the group. But I do want everyone to be involved. I don't want somebody to be like, okay, you guys take data, I'm just doing homework. You can do homework in between, but I want everyone to be involved when you're taking data, just so you're aware of the process. It is very boring, I admit this, but what we want to do is to confirm that what I am saying about radioactive decay is what really happens. If the theory is correct, then on the semi-log paper, you should be able to make it, take a ruler and draw a straight line to fit the data. On this paper, you'll also take a ruler and draw a straight line to fit the data. One of them will look like a better fit than the other. You're going to find the slope for both of them. This one, you're very comfortable finding the slope with, probably. This one here, not so much. So let's just put a random line on here. Let's say my line goes like this, and I want to find the slope of that line. First things first, what will lose me points for sure? Okay, not drawing a straight line will lose you points, that's true. For finding the slope, what will lose you points? If I use my data points to find the slope, right? Because I want to find the actual line, not just two of my numbers and throw the rest away. So you want to find an easy to read point near the beginning and end of the line. So I look at this and I say, okay, this here, here's a good color. Well, here's a better color. Right here, it appears to be going through 1, 2, 3, 4, 5, 6, 7 minutes. And the vertical is 3,100. So that's near one end of the line. Then I go to the other end of the line and look for another place that's easy to read down here. So I look and try to find a place where it's crossing over and I can easily read it. I am not very satisfied. This here is a little bit high and this one here is a little low. Well, you can see the difficulty in finding a point to read. Okay, that there's a pretty good one. And so for that one, I'm going to read its time and its. So, you put it to stop as soon as your alarm goes off, and then you write down that number. Okay, is everybody, well, not everyone's done with the background. So I got my 2 points. Now to find the slope, what's the normal method of finding slope? Rise over run. So we still do that. The slope is the rise over run. But in this case, the rise was the logged axis. And so we do natural log of y2 minus natural log of y1 over x2 minus x1. Except for one little thing. You can't do natural log of y2 or natural log of y1 because those have units and you can't do the natural log of something with units. But that's okay because this is exactly equivalent and takes away the unit problem. So for my numbers here, that would have been natural log of my y2 was 3,100 counts per minute. My y1, well, just make sure you remember which one's which, and it doesn't matter which one it is. 470 counts per minute. And then it would be 7 minutes minus 79 minutes. Put that in my calculator. Of course, the denominator there is a negative number, so I'm going to have a negative slope. But that gives you my slope. And so the equation for the straight line here should be r is equal to r naught e to the minus lambda t, where that lambda is the slope. So you're finding the slope is the decay constant from this graph. Once I found that slope, I'll come back here to the lab guide, and we're going to calculate from that decay constant what the half-life is. The time when I should have half as much remaining as I started with for my sample. And so I just take that and I say, okay, half-life is natural log of 2 divided by the decay constant. Decay constant is minus the slope. And so calculate your half-life. Now you just have a few questions here. 4 questions to answer based on that graph, or on the 2 graphs, because you have also find the slope of this graph. And so just answer those questions. It asks you for the accepted half-life of indium. Google. Look it up on Google. You will get more than one half-life for indium-116. You have to look at those and think about this experiment. The time frames of the 2 are very different, and it should be clear one of them is not applicable. And then It asks, how would this experiment be different if you used neutron-activated cobalt-16 instead? So look up what the half-life of cobalt-16 is. See how that compares and answer the question. Okay, does everybody have the backgrounds done? Okay, everybody needs to take out anything that you ever plan on sticking in your mouth before I come back